one of the primary uses for a derivative is to identify the max or min for a function. So let's say I have some continuous function on the interval from a to b. Assuming this function is continuous, then it must be true that this function achieves a maximum and a minimum point along this interval. And what we'll notice from this drawing is that at the maximum or minimum points, and this is something we've previously discussed, there are horizontal tangent lines there. Let's call this point C and this point D. We can say horizontal tangent lines have slopes of 0, and therefore, if our function we'll call f of x, we can say f prime of c equals 0 and f prime of d equals 0. And when the derivative at that point equals 0, we can see that we have a max or a min. So let's make the distinction that f of c and f of d represent what we call extreme values. Extreme values are going to be our max and mins. So the question we want to ask ourselves is, do we need to consider anything else other than the fact that at a max or min, the derivative equals 0? So again, that's something we've discussed before, but are there other scenarios that we have to consider? And the answer is yes. So I'm going to present two more scenarios that we have to be cognizant of if we're trying to identify a max or a min. The second scenario. Let's say we have some function on the interval from a to b, but there is no horizontal tangent. So we have something like this. We might say, well, as long as the function's continuous along this interval, we know that it has to achieve a maximum or minimum value. So where are they if there's no horizontal tangents? Well, they're going to appear at the endpoints. So in the event that we have a bounded interval, we must consider the endpoints as a location for a max or min as well. So it's not enough just to consider whether the derivative equals 0. We must also consider endpoints. And there's also a third scenario where I might have corners and cusps. And what we see here is there are clear max and mins. The only problem with this is that we can't calculate a derivative at corners and cusps, as we previously discussed. So determining where the derivative equals 0 is not sufficient enough to identify the max or min when we have a cusp. But what we do know, or a corner, what we do know about the derivative at a corner or a cusp is that the derivative is undefined. So if this is c and this point is d, then we know that f prime of c does not exist, and here f prime of d does not exist as well. So that is something we should also consider when determining whether or not we have a max or min. Does our derivative exist at that point or not? Let's consider that for potential extreme values. So what we're going to do now is come up with things that must be true if we've identified an extreme value. So we're going to say if f is continuous from a to b, and f of c is an extreme value, and we know an extreme value must be reached on an interval assuming that the function is continuous. And an extreme value, again, is a max or a min. And c is an element of that set from a to b. So it's part of that, it's inside of that interval. Then, one of the following must be true. So if we know we have an extreme value, then one of the following three things must be true. The first is we know at that point the derivative is equal to 0. And that's where we have the horizontal tangents. But we said that doesn't always tell the whole story. There are other maxes and mins that can be found that don't have derivatives equal to 0 at them. So the second thing we should consider that is a possibility is that that C value, where the extreme value occurs, could be actually one of the endpoints. So C could equal A, or C could equal B, meaning that the extreme value is at an endpoint. Sometimes endpoints will refer to as the boundary points. And then third, if neither of those two things are true, well then the third thing that must be true would be that the derivative at that point does not exist. And that will occur when we have those corners or cusps that are representative of our max or mins. And again, only one of these things must be true, assuming we have an extreme value. Now, why is this important to know? Because in the event that we want to find an extreme value, I can check to see which one of these things is happening, or I'm going to review all three of those things to identify where I could potentially have a max or a min. And that is where the first derivative test comes into play. So we'll jump over to that. Before we jump into the first derivative test, let's just review what the first derivative tells us about our function f of x. Remember that first derivative represents an instantaneous rate of change. And if we have an instantaneous rate of change that is positive, we will have a function that is increasing in value. So to determine where f of x increases, I'm looking to see where f prime of x is greater than 0. And f prime of x being less than 0 will indicate I have a negative rate of change, and therefore the function is decreasing. Now, why would it be important to know this? Because if I can identify this change in behavior, I will then be able to identify a max or a min. Because if we go from increasing to decreasing, we have a max. And if we go from decreasing to increasing, we have a min. Or if we're at an endpoint, so let's look at a left endpoint and a right endpoint. Left endpoint. If it's decreasing from the left endpoint, that means we had a maximum at that point. If it's increasing from the left endpoint, that implies you had a min at that left endpoint. Right endpoint. If it's decreasing to the right endpoint, then we have a minimum at that right endpoint. And if it's increasing from, or I should say increasing to, we have a max. And when I say from and to, we're working from left to right. So for instance, if we have our picture of our function with a bounded interval, so it's closed, we say something like this. From that left endpoint, you see that it's increasing from there. Therefore, that's why you have that min there. Then you say it goes from increasing to decreasing, there's your max, which we said before. Decreasing to increasing, there's our min. And then increasing to the right endpoint, that's why we have a max there. Okay, so we're working left to right when we're evaluating that increasing, decreasing behavior. And that's how we can use that to determine where we have maxes and mins. Now we just have to figure out, well, where does the function actually increase and decrease? And that's where the first derivative test comes into play. So this is to identify those extreme values. The first thing you want to do is identify where you potentially have extreme values, and where those extreme values potentially are called the critical points. So you need to identify the critical points. So off to the side, the critical points. How do you identify them? First, their potential extreme values. So not all of these will actually be a max or min. They're just potential extreme values. We're going to have to analyze parts of the derivative to determine whether or not they are extreme values. Once I've identified the potential extreme value, or the question now is how do I identify? So to identify, we already know, or we've already discussed, that if I do have an extreme value, one of those three conditions we discussed has to be true. So to identify, what I want to do is consider all three of those conditions to populate my list of critical points. So to identify, we want to know where does the derivative equal 0? Because that's where I'll have horizontal tangents, and that's where I could potentially have a max or a min. The second thing, check your endpoints. We'll just say consider endpoints. So endpoints are automatically critical points, but it's only if we have a bounded interval. So if the problem doesn't have a bounded interval, then we're not going to consider any endpoints for potential critical points. And then lastly, we discussed we could have max or mins when the derivative is, instead of c, let's call it x, when the derivative does not exist. So considering these three things will populate our list of critical points. Once we've identified the critical points, we are going to make a sign chart for the derivative. And once we've made a sign chart, we analyze the sign chart to determine where f of x is increasing and decreasing, and thus deciding where our max and mins are. So that is the first derivative test. So now let's look at some examples that take this into account. Where is f of x equaling x squared minus 6x increasing or decreasing? If I want to know where a function is increasing or decreasing, I'm going to analyze its first derivative, and the sign of the first derivative will tell me if I'm increasing or decreasing. So what is the first derivative? It's 2x minus 6. Now, I want to be able to identify critical points from here. Critical points are where the derivative equals 0 or where it's undefined, or endpoints. This interval, or this function, is not bounded. This has a domain from negative infinity to infinity, so it's unbounded on both ends. Also, the first derivative will never be undefined, so all I need to know is when will this first derivative equal 0. So 2x minus 6 equals 0, x equals 3. So my critical point is at 3. Once I've determined critical points, I set up a sign chart for the first derivative, and I put my critical points in order. Imagine this is a number line. There's only one critical point for here. And I decide in these regions, so there's two regions here, I put a sign whether or not it's positive or negative in that region. To do that, choose any value less than 3 for the left region. And you must evaluate the derivative, not the original function. This is a sign chart for the derivative. So let's say I choose 1. When I plug in 1 to my derivative, I get a negative number, which means the sign in that region of the sign chart is a minus. To get the sign in the other part, choose a number greater than 3 in this case, let's say 4. And that will get me a positive output. Again, all I care about is the sign because I'm making a sign chart. And if the derivative is negative when it's less than 3, then I know the original function is decreasing on that interval. And if it's positive, I know it's increasing on this interval. So to answer the question, f of x is decreasing from negative infinity to 3 and increasing from 3 to infinity. And if we wanted to add a second part to this question, because it goes from decreasing to increasing, we can also identify that 3 is a minimum. Next question. if we were already given the critical points of 3 and 4, and this function is working on a closed interval from 2 to 5, so this notation means the interval is bounded from 2 to 5, 2 and 5 being included in the interval, therefore 2 and 5 are now critical points. If this was parenthesis 2 to 5, then 2 and 5 are not included in the interval and therefore do not need to be considered. It's only if the endpoints are included in the interval, meaning it is bounded. Okay, so make sure you consider that interval notation. You see brackets include the values as critical points. The corresponding sign chart is given. Determine where f of x has extreme values. So we put our sign chart for the derivative. You can see that the critical points of 3 and 4 have been given, and then 2 and 5 were added in because those are endpoints, and they are included in this function. So analyzing from left to right, from 2, because the derivative is positive, that means f of x is increasing, still increasing, then decreasing. It's increasing from 2. If it's increasing from 2, then we know f of x has a minimum at x equals 2. Then, for the critical point of 3, notice how it goes positive to positive. So it did not change signs, which means 3 is not an extreme value. It didn't go from positive to negative or negative to positive. So if it doesn't change signs, that means 3 is not an extreme value. However, on the next critical point of 4, it goes from positive to negative, which would imply that we have a max there, because it's going from increasing to decreasing. And then it is decreasing to 5. So if it's decreasing to 5, that means 5 could be considered a minimum. So we'll add that to our list. And there's our analysis of the sign chart and the extreme values related to this function. C, find any extreme values for that function y. Extreme values require us to analyze critical points, which will be found from the derivative, or endpoints. By the way, this is an unbounded function. This domain is negative infinity to infinity. They don't give us a bounded interval, so I don't have to check endpoints. So endpoints will not be included in my critical points on my sign chart. Calculating the derivative, we're going to get x squared plus 4x plus 3. This derivative will never be undefined, so I don't have to know when it does not exist. The only thing I'm looking out for is when does this equal 0. Factor that, you'll get that x equals -1 and x equals -3 are your critical points. We make a sign chart for the first derivative. We add our critical points in. And this is a number line, so go from least to greatest as you list them. We want to apply a sign to each region. So select a number in that region and evaluate the first derivative at that. Remember, this is a sign chart for the derivative, so you don't want to plug into the original function, but rather the derivative. So I'm going to do -4. When I plug in -4, all I care about is the sign. When I plug in -4, 16 minus 16 plus 3, we're going to get plus. Let's evaluate the derivative at -2. When we plug in -2, we're going to get 4 minus 8 plus 3, which is a negative number. And then let's evaluate the first derivative at 0 to get the rightmost region. When we plug in 0, we get a positive number. So we're going to get positive, negative, positive. What that means, again, is that we are increasing, decreasing, and increasing for y. And if it goes from increasing to decreasing, we have identified a max here. Decreasing to increasing, we have identified a min. So there are extreme values. We're going to say max at x equals -3 and a min at x equals -1. Now, before we jump into what the second derivative tells us, we should discuss the idea of global versus local. Global, max min, the global extrema, meaning global extreme values, mean the absolute highest or lowest point in the domain. we'll say absolute max or min. Stay consistent. Local just means it's the highest or lowest point in some open interval around that input. So it's the max or min on some open interval around that input. And when we say some open interval, just think some small region around that point. So just a quick visual. This point here is the absolute or global max because it's the highest point on the entire domain. Here we just have a local min because it's not the lowest point. Those arrows indicate it goes down forever. So this is just a local min. And this would just be a local max. It's the highest point in this little region here. Now the question is, if we don't have the graph, how do we identify global versus local? Well, there's a couple things you need to think about. So identifying global extrema. If you have multiple max or mins, so we'll say and or mins, then you need to compare the function output at the location of those max or mins to determine which one actually has the greatest output or the lowest output, whatever you're looking for, whether it be max or min. Then compare function output at those extreme value locations. Okay, so you have two maxes and you want to know which one's the global max. You have to plug both of those values into the actual function to get what the function output would be. So we're not plugging into the derivative. Okay, so we identify where they are using the derivative, but then to identify the global max or min, you need to evaluate the actual function and compare output values and say, all right, this one has a larger output than the other, so it must be higher than the other one, and therefore that's the global max. But something you also want to consider is end behavior if unbounded function. This one's a little sneakier. Okay, so consider the end behavior if the function's unbounded. You can use your sign chart for that. So like if you have a sign chart with f prime and you have, say, 3 and 5 and 6, we'll say, and it's negative, no, we'll say positive, negative, positive, negative. So this thing is increasing, then decreasing. Once we hit 3, then decreasing to increasing at 5, then increasing to decreasing at 6. So this is where 3, 5, and 6. Let me lower 6 to get the point across. You might identify this is your only min, so you may want to say, oh, that must be the absolute min. But it's not actually. Because of this end behavior, it goes down forever. Now, how do we know it goes down forever? Based on my sign chart for f prime, that thing's unbounded. So that thing is going down forever to the left. It's increasing up to 3. And then after 6, it's decreasing after that. So it's increasing to 3, so I know it's coming up. Then after 6, it's decreasing. And again, because it's unbounded, I know it goes forever in those directions. So it extends down. So this actually isn't the lowest point, but it's rather just a local bit. So if you're ever wondering, when you have an unbounded function, is this actually the global max or min? Consider the end behavior. Now, in the case of the maxes, when I compare those two, because I know the ends of the graph go down forever, well, then this would actually be the absolute max. Okay, there's no issue there. But if we had another point, like if I just extend this graph and have it go the other direction, so let's say we added in another min. Well, first of all, both of these mins would now be local because this right end of the graph goes down forever. So this is still a local min, even though it's lower than the other one. And then because the left side goes up forever now, then this is no longer the absolute max, but rather just a local max. So it's important that you consider end behavior when analyzing whether or not you have global max or mins. In the event that it's bounded, well, then comparing outputs of all your maxes and mins will be enough. So make sure you add on the end behavior consideration in unbounded functions. So what does the second derivative tell us? Now, once we know what the second derivative tells us, we'll be able to use the second derivative test, and that will conclude the video. The second derivative is the first derivative of the first derivative, right? So the second derivative is the derivative of the first derivative. If the first derivative told us where f of x was increasing or decreasing, then the second derivative should tell us where f of x is increasing, or f prime of x is increasing and decreasing. Now, what does that reveal to us? Well, if f prime of x is constant, that means you have a linear function. That means your rate of change stays the same the entire time. There's no change in the rate of change. Okay? So if f prime of x is constant, you have a straight line. But if f prime of x is increasing or it's decreasing, then what that does is create a bend in the curve. So the second derivative, what it tells us about f of x is it tells us how the function bends. So what does that actually look like? Well, if f prime of x is increasing, I think the slopes of the tangent line are becoming more and more positive. So as we go along, the slopes of the tangent lines become positive. So this would be a case where f prime of x is increasing. Here's a case where f prime of x is decreasing. And the reason why, again, you can add in tangent lines at various points and see that the value of the slopes of those tangent lines are increasing in value in this example. And they're decreasing in value in this example. So if f prime of x is increasing or decreasing, it creates a bend in the function. We call that bend its concavity. And something will be concave up when f prime is increasing. Concave up when the first derivative is increasing. Now, how do we tell when the first derivative is increasing? That's when the second derivative is positive. So the second derivative will reveal to us the concavity. Again, concave up, something like this. Concave down will be when the first derivative is decreasing. And we'll know when the first derivative is decreasing when the second derivative is negative. And that is where the second derivative can reveal the concavity. Something like this. Now, we can have functions that change concavity. And when functions change concavity, we've just identified what's called a point of inflection. So we could have something that goes concave down to concave up. Oh, poorly drawn. Or concave up to concave down. that transition point in concavity is our point of inflection. So something like right here, or right there. Okay? Now, how do we identify the point of inflection algebraically? We're going to look to see where the second derivative changes signs. As the second derivative is positive, we know we have concave up and negative concave down. So if I can see where it changes signs, that will reveal where I have a point of inflection. Therefore, we can make a sign chart to identify where we have concave up, concave down, and points of inflection. Points of inflection we are going to consider as or I should say points of inflection can be found by considering critical points for the second derivative. How you find those critical points is the same way we found critical points in our first derivative test. So a couple of quick examples. Where is this function concave down? So if I want to know about concavity, I'm going to analyze the second derivative. So first derivative is negative 2x. The second derivative is just negative 2. So the second derivative is always negative, which means it's always concave down. There is no need to make a sign chart on this. There are no critical points to be found here. The second derivative never equals 0, it's never undefined, and it's not bounded between 2 points, so there's no critical points. And that should make sense if you think about what this graph looks like. Negative x squared plus 5 will look something like this, and you can see that that graph is always concave down. Where is this function concave up, and where is the point of inflection? So dealing with concavity and points of inflection will require me to find the second derivative. Now, because the second derivative isn't constant, I want to consider where this thing has critical points. So I'm making a sign chart for my second derivative. The critical points that go on that sign chart need to come from the second derivative equation. And they can occur when the second derivative equals 0, when the second derivative does not exist, or at endpoints. This thing is not bounded between any 2 points. Its domain runs from negative infinity to infinity. It's never going to be undefined, so I don't need to worry about when the second derivative cannot be calculated. So I just want to know, when does this thing equal 0? So f double prime will equal 0 when x is negative 2. Let's make a sign chart in relation to this. So I'm going to choose some points in each region. So let's do negative 3. Again, this is a sign chart for the second derivative. So plug values into the second derivative. When I plug in negative 3, I get a negative value. When I plug in 0, I get a positive value. That means that f prime is decreasing and then increasing, which means f is therefore concave down and then concave up. And because of that, the change in concavity, or the change in the sign for f double prime, indicates that we have a point of inflection at x equals negative 2. And then where would you say it's concave up? It's where the second derivative is positive. So it's concave up from negative 2 to infinity. Now that we know, we can identify where the function bends or how it bends based on the second derivative and analyzing the concavity, along with the fact that we can identify where potential extreme values are using critical points of our first derivative. We can combine the two to come up with the second derivative test to help us identify max mins. So the second derivative test. Requires you to do the following. Identify critical points from the first derivative. Then, once you've identified the critical points, what you do is evaluate the second derivative at those points. So rather than using the sign chart to determine where the function goes from increasing, decreasing, or vice versa, what you can do is find critical points and just plug those critical points into the second derivative. What that does for you is when you plug it into the second derivative, you've just determined what concavity is occurring at that point. And if you know the critical points represent potential maxes and mins, and therefore evaluating the second derivative and determining its concavity, you will be able to identify a max or min. So if C, or x equals C, is a critical point, and f double prime of C is greater than 0, the second derivative is greater than 0. Again, a reminder, that means you're concave up, which means you have a minimum at that point C. If the second derivative is negative at that point, you are concave down. Would imply you have a maximum. And if it equals 0, well then, you have neither. In fact, you potentially have the point of inflection. So, greater than 0 implies concave up. If you already know that that is a critical point, that means you have a min. If you evaluate the second derivative and it's negative, you have concave down, and you just identified a max.